Hello and welcome everyone. My name's Peter Robinson. This is the Ethereum Engineering Group Meetup. And Dr. Sandra is here today to tell us about the possibility of moving from stakers with 32 ETH to maybe having a lot more stake and what the ramifications of that might be. So welcome, Sandra. And I hear you're going to introduce yourself via your slides. So
Yes, I'll do
why don't
that.
you then lead off?
Okay, sure. Let me just share my screen and just confirm that you can all see my screen.
Yes.
I can see thumbs up there from Joanne as well and and Peter.
Yeah, we can see them.
Good. Okay, so I'm talking about some research we were doing on proposer selection, and I'll go through the EIP that I mentioned here as well. So as Peter mentioned, I'm Sandra and I work for Consensus Software, and I've been with the R&D team there now for approximately 5.5 years. An interesting little fact is Peter was the one who hired me. And the research I'm presenting today is actually joint work with Kerry Mengerson, Patrick O'Callaghan, that's on the call today as well, and Anders Madsen, who's from Denmark at Aalborg University. So just a very brief overview of the talk today. So I'll provide a bit of context for our research, and then I'll talk a bit about EIP-7251, as the title alluded to. So because this research concerns that EIP, and then what was the motivation for that EIP, then we'll go into the actual proposer selection modeling, and I've got included some references and links to blogs, and then just, and then we'll kind of wrap up. So just to provide some context here. So the key issue here, the problem statement essentially, is that in the Ethereum beacon chain protocol, there's sort of uncertainty about the future computational load that nodes will have to handle. And the load is roughly proportional to the number of active validators, and the attestation processing time, epoch transition processing time, and memory requirements. And they're all kind of scanned linearly with the active validator count. So basically, this problem was identified by Vitalik, and it prompted him to write a blog post on how one could potentially cap the number of validators. And this blog post was the initial motivation for our research. And we collaborating with Barnaby Mono from the Robust Incentives Group, they just call them the RIG group at the EF on this project. And he mentioned that basically solving this dilemma is a precursor to achieving single slot finality. However, when I started looking into Vitalik's musings on the subject, I suddenly discovered that his blog post on validator set size capping had vanished. But instead, Vitalik had incorporated this problem within the larger context of single slot finality, which really was the motivating, the sort of driver of capping validator set size. So basically, that is then what we had to do. We had our initial research question was, what is the preferred strategy for capping validator set size? So Vitalik proposed several potential options, basically super committees. So instead of basically all of the validators participating in each consensus round, only a medium-sized super committee of tens of thousands rather than all of them. And that will allow the rounds of consensus to happen in just a single round. The other proposal he had was to cap the validator set, which is where our focus was, rather than the super committees. So there were two strategies that he suggested, one being order-based capping. And so in this, with this sort of strategy, it's either the oldest validator stays. So if it's reached the cap, then basically if someone leaves, the oldest validator would stay. The other one is the opposite, the newest validator stays. And then there's the other strategy is economic capping, and that can be done basically through capping the total ETH that's deposited or the total validator count. So this EIP, or the Ethereum Improvement Proposal, was to increase the maximum effective balance. And basically that sort of happened at the same time as we started our research. And a teacher who at the time worked for the EF, but has since left to work elsewhere, he published a post that attracted a lot of attention, and giving us a more sort of specific path forward to reduce the active validator set, as Vitalik had mentioned. So he also highlighted here basically that our validator set is large, but it need not be that big, because he reckoned it could effectively be reduced by half. Because a lot of stakers that stake in Ethereum would be running more than one validator. So really, it's just unnecessary duplication of tasks, of messaging that's going through. So in that little diagram there, which I took from his blog post, you can see there you've got one staker that runs 3, and the others are two single validators. So Mike Noida, also from the Ethereum Foundation, then started articulating Aditya's thoughts in what he termed a modest proposal to increase the maximum effective balance. So this was the means by which they thought they could contract the validator set size, because instead of single validators, you could combine 2 or more together into a single validator. I've included links to all these posts in my slides, and I think Peter will share them with you later. So his modest proposal, as he termed it, was the start of formulating what would actually become EIP-7251. So it appears to be a very simple objective to reduce the number of validators by increasing the maximum effective size to 64 times what it is currently. So currently it's 32 ETH. So proposing to change it to 2048. On the assumption that the large validators will choose to consolidate some or all of their validators into larger validators. The other interesting sort of offshoot of this is that, say people do not or are unable, like say if you solo stake, you are unable to you combine more than one validator because you haven't got enough ETH to stake, or you don't want to stake more ETH. It also then effectively enables auto compounding, because your limit of what you can stake is much higher now. So any rewards earned can also then earn, basically when you earn rewards by participating as a validator, you can basically earn more. But just remember that the increments though are in 1 ETH. So providing your rewards have accumulated to 1 ETH, that then instead of 32 ETH, it'll be 33 ETH. So anyway, so effectively, this has now been written up consequently by, so Mike Noida was then officially the champion of this EIP, but it was also co-authored by by several other people. And although this is an EIP in its own right, it is also dependent on another EIP being implemented, EIP-7002. And what this EIP does is it enables you to trigger a partial withdrawal from the execution layer. Now I'll discuss a bit more down the track why this is important. So what these, so as part of the spec changes as a result of, if we're going down the route to implement EIP-7251, some of the things that are required. So there are 3 constants that are, one will change. So obviously the maximum effective balance will change from 32 to 2048, and 2 new ones are being introduced. So we've never had a minimum activation balance, because basically the maximum effective balance of 32 was also what you needed to be able to start staking, to run a validator. But now there's going to be a discrepancy between your minimum activation balance, so that's remaining the same. So that's going to be 32 ETH. And also the withdrawal prefix will change from 0x01 to 0x02, and then the protocol will basically know that this is a compounding validator, or a consolidated validator, and it does not adhere to the rest of the sort of rules that apply to the 0x01 validators. Within the features there that they clearly define, the spec is sort of mainly stable now, but it's still a little bit in flux. For example, there you'll see with feature number 3, talking about custom seedings, the discussion I can see at the moment around this EIP is that probably won't be included, because it'll add a lot more complexity to the code base. And it doesn't seem there's no real traction there for people wanting to implement that. And this is where that EIP-7002 will give this sort of functionality already, because with a custom seeding, you'd basically be saying, well, once my validator gets to this, I want it to be part of this. So what happens every night is there's a continuous sweep of all the validators, and any balances above 32 ETH are basically withdrawn into the validator's account. But once they're auto-compounding, obviously that's not going to happen until they reach 2048 ETH. So if you've got a stake, a balance, effective balance much lower than that, but say it's 64 ETH and you now, it's gone up to about 67, and you want to actually get that, use that 2 ETH elsewhere, you can actually then initiate a partial withdrawal from the execution layer, and that's why they thought they could put in custom seedings, and then you'll have a custom seeding, say at 66, and if it's any more than that, it'll withdraw. But it just seemed overly complicated, and this, the changes coming through this is already quite complex. Anyway, because EIP-7251 came along while we were looking at sort of capping validator sizes using one of the other sort of proposals of Italic, we decided to update our research question to basically say that if we allow for this varied consolidation strategies by large stakers, can we confirm that apart from an expected slight increase in processing time, there's no adverse effect on proposer selection for stakers and validators? So that is where we changed our focus to. And also, we just wanted to make sure that stakers were not adversely affected by this change. And so it's especially with regards to solo stakers, their stake will be so much smaller. We just wanted to ensure that they are not adversely affected. However, there is, as I mentioned briefly earlier, there is a benefit to them in as far as the fact that they'll be able to compound. But also, you know, what does that mean for large stakers? Is one consolidation strategy better than another? Anyway, just a slide with some links if you're interested in looking at some of the analysis that's been done to date. There's a lot that has been done, and more is done all the time. Anyway, you'll be able to click onto any of those links because the slides Peter will make available after the talk. So before I dive into the actual analysis and modeling, just want to know if there are any questions so far. I haven't checked the chat. If not, I'll carry on. Right.
I think it's all been very clear.
All right, good. So with proposer selection, analysis and modeling. So first of all, looking at this one thing that was mentioned is a slight increase in proposer selection time. We thought, well, let's have a look at what that would be. So here we is a sort of negative binomial graph, and what we find is that the median value, so basically we're assuming that our entire validator set are people with 32 ETH effective balance. So the probability of any one of those passing the proposer check is 0.016. So we use that to then work out the the number of basically iterations or failures basically before we have a successfully chosen a proposer for the next block. The median value for this was 43. So essentially, half would be less and half would be require more iterations. And then I thought I'd just look at a few as other sort of values, like, what is the probability that fewer than 100 will be required? And that's 80%, which is pretty good. But then there's still 20% that we might need more than 100 iterations. Once we look at the probability that more than 200 iterations will be required, we're looking at about 4%, more than 300, 1%, and then it sort of goes down, as you can see, quite rapidly. So really, these additional iterations should not have any noticeable effect on processing time because So then basically, we're looking now at the actual process of selecting a proposer. And that involves a few steps. So first of all, basically the validator set with all the validator indices comes along, it gets shuffled. Then the first validator index on that set gets selected as a candidate. And then we perform a check to say, has this validator passed the test? The shuffling of those validator indices is done by a technique called swap or not shuffle. And that is a link to the actual method that computes the shuffled index. And again, that's a link that you'll be able to click on if you're interested. And also I've put a reference in the references to the paper that explained this technique in detail. Then to actually choose the next proposer, also there's a link to that procedure in the slides. So as I said, I've just said that. So anyway, so obviously if you then go through this process, you shuffle, got the first validator, do the check. If it passes, yes, fine, then you move on. You've got your next proposer, your proposer for the next block. If not, then you just iterate and you do the whole process until you find a successful validator. So one of the things that happens as part of this is there's an equation where we need to basically generate a random byte value. So that's used in our equation, and that will be, I'll show you in the next slide. So we need to, as part of this proposer check, we need to generate a random byte. And this is the code that basically generates this pseudo-random value. And we ran this code to generate values for, I just decided on a fairly large validator set random size of like 716,800. And then we superimposed the uniform distribution across those values that the random byte can take. And as you can see, this clearly resembles a uniform distribution, which also then supports the assumptions made in a lot of the analysis that you'll read, if you read some of the analysis where they just assume that the random byte is uniformly distributed across that range. And we also then confirmed it statistically through a QQ plot. So with the, this is the basically the code check there. So it says if the validator's effective balance is greater than, if it is, if the, sorry, if the proposer's effective balance times the maximum value that the byte can take, which is 255. If the effective balance times 255 is greater than or equal to the maximum effective balance times whatever random byte was generated for that validator, then that person gets to pass the test. So we can just rewrite that a bit. We see that the randomly generated value needs to be less than 255 times the effective balance divided by the 255 times the effective balance divided by the maximum effective balance. So clearly, if the validator keeps their effective balance at the maximum effective balance, then they will always pass the check. And if we just look more generally, we can calculate the probability that a proposer check will pass by taking effective balance divided by max effective balance. So we can also then see this. I thought it's quite helpful to just do this as a show this on a graph, and I've picked a few sort of consolidations of validators, so having different consolidated by 2 or 5 or 10 or whatever validators into one, and the probability of them passing the test. So it kind of varies from 0.16 for a 32 ETH validator to 1 for a fully consolidated validator, which is 2048. So the ones that I'm using in the example are basically the ones that I've plotted there. So with the increase in maximum effective balance, we see that the probability of a 32 ETH validator being selected and passing the proposer check will fall from what it is currently, if we assume the validator set size that I used. It'll go from basically 1.395 times 10 to the minus 6 to right down to 2.18 times 10 to the minus 8. So when you look at it, it just seems obvious that solo validators would be worse off with such a reduction in passing the proposer check. But we also got to remember that if the validator set remains unchanged and all the validators are still 32 ETH, then all of them will have a pretty small chance of being accepted. So it could be that even that there were other validators that didn't pass the test, and by the time this validator comes along, they actually pass the test. And we can calculate this probability. So let us then calculate the probability that the validator is chosen not just at the first iteration, but at all subsequent rounds. So if we state this a little bit more formally, we're basically looking at the probability that a 32 ETH validator who's selected at a round I, for example, means that the previous round, so 1, 2, through to the previous round I minus 1, were all unsuccessful, and then there was the successful one. And so we just calculate that by summing over all the possible rounds that this validator may have been selected. Yeah, so I mean, just simply if a validator is selected as the next block proposer in round 3, then another validator was selected at round 1 and at round 2. And doing this, if we sum across all rounds, the probability of a solo validator being the next proposer is actually exactly the same as in the previous slide. It's also 1.395 times 10 to the minus 6. However, I was thinking that, when EIP-7251 goes live, it's kind of pretty unlikely that the validator set would remain exactly the same, because it might be interesting then to look at a bit more of a realistic scenario. So before we look at the scenario there, any questions? If not, let's dive in. So let's look at an example. And what I did is I said, I actually asked Vitalik, and it's amazing he responded, and to ask him, if he could group the type of stakers that participate in Ethereum, what sort of categories would he put them in? And he suggested that there'd be a group of that we could call small scale solo validators, who'll have typically 32 to a few hundred ETH. Then large scale individual validators, and there are some that have got run more than 1,000 validators. And then there are large scale institutional solo validators too, where companies stake their own ETH. And then we've got decentralized staking pools and semi-decentralized staking pools such as Rocket Pool and Lido. So if we assume up at the top, you'll see 716,800 active validators, and we split them against these different staker categories. And each category, I mean, I just made this all up just for an example to work with. So, and each category we say has got a different sort of consolidation strategy. And I used a few different combinations. So had some single validators, single stake validators, then twofold validators, 5-fold, 10-fold, and 30-fold, and then the maximum where someone has, or where people have decided on the maximum, so 64 lots of 32 ETH. And then, as I said, for each of those staking categories, we're assuming that they have the same sort of strategy. And in the diagram, you can see the proportion of validators that they have for each of the validator types. So then it shows just in the calculation how many validators then, and then you can see in the sort of turquoisey color that the consolidation set has now gone from 716,800 to 328,910. So quite a large contraction of the validator set. So basically what we did is we thought we'd do Bayesian network modeling to play around with these values and see how the probabilities work out. So before I describe the Bayesian network model we built for a proposer selection, I thought I'd just give depending on time, how we're going for time, I think it's okay. I'll just give a quick overview of what a Bayesian network is. I know that Joanne's probably heard this many times and probably also Peter. So anyway, please bear with me. So basically, it's what we call a directed acyclic graph. So as you can see there, you've got nodes of those, the round things there are nodes, and then you've got directed edges. In other words, you don't have any loops. So you just have the edges that connect the nodes in the group. And it's a type of probabilistic graphical model. And I will sort of demonstrate where they fit in. And then we'll have a look at, why is it a Bayesian network? And we'll look at conditional probability tables, because that is why it's essentially considered to be Bayesian. And also talk about two important strategies, statistical properties that they have. So People often mention that a Bayesian network is a probabilistic graphical model. So just taking a quick step back to get some context of where BNs fit in within the framework of probabilistic graphical models. So they can basically be broken down into those that have directed edges, as the Bayesian network I just showed, sort of between the variables in the graph, and those that have undirected edges, such as Markov networks, or perhaps better known as Markov random fields. And then we also have hybrid graphical models, and they're hybrid in the sense that they include both directed and undirected edges or links between the variables. And like a chain graph would be an example of that. So the Bayesian networks obviously fall under the directed graphical models. And then we've got a couple of specializations of a Bayesian network, such as a dynamic Bayesian network and an object-oriented Bayesian network. And the latter is the approach that we will use. So who is Bayes? He was born in 1702. His father was one of the first 6 publicly ordained nonconformist ministers in England. And interestingly for him, because the practice with nonconformist ministers at the time was that Bayes was educated privately. So there's speculation that he was tutored by an eminent French mathematician, Abraham de Moivre. I don't know how you pronounce it. He's French. And he had to flee France due to persecution of Protestants. And this guy was also friends with Edmund Halley and Isaac Newton. So pretty interesting times he lived in. The thing I just find quite bizarre is that Abraham de Moivre, he actually correctly calculated the date of his death. When I read more about it, I think he kind of almost willed himself into, following his theory. Anyway, Thomas Bayes became an ordained minister, and then Richard Price was a friend of Reverend Thomas Bayes, and he published his work Bayes's work in 1763, 2 years after his death, actually, and he presented it to the Royal Society of London. And it was called An Essay Towards Solving a Problem in the Doctrine of Chances. And it's also known more generally as a method to solve the problem of inverse equations and inverse probabilities. And basically, this is the Bayes theorem, as we all know and love. And the central idea of Bayes theorem is we start with a prior belief about the probability of a hypothesis, so of the probability A. And then we revise our belief to take new evidence B, which is information or data, into account, and that may confirm or contradict the hypothesis. And we therefore look at the probability of this data, given that the event or the hypothesis is true, and we call this the likelihood. We then divide by the probability of the data to produce the posterior belief. And this simple equation provides us with a very intuitive way of dealing with probabilities, and we can reframe questions of chance, update probabilities with data and evidence. The other thing that I mentioned is the conditional probability table, which is also sometimes referred to as a node probability table. So for the node in our model that you'll see shortly is the proposer for the next block. So we've got 2 parent nodes, validator type selected as next candidate and proposer check. So looking at the table, you can see if the validator was not selected, then whether or not the proposer check passed or not is immaterial. It cannot be the next proposer. So the only time it is the next proposer is when the validator is selected and it passes the test. So for the statistical properties, we'll first look at the Markov properties. So the first order Markov assumption is that if we know the present, then the past has no influence on the future. And related to the Markov property is this concept of a Markov blanket. So a node's Markov blanket includes all its parents, its children, and its children's parents. And the interesting thing is that it can be shown that a node is conditionally independent of all other nodes, given values for the nodes in its Markov blanket. So for example, in this little diagram, if we look at node C2 there, you can see that the parents are C3, C4, and C6. C2 has only got one child, which is the outcome of interest, and the parents of that child is C7. So basically, these 6 nodes then would be the Markov blanket for node 6.2. So the only other interesting statistical property is a d-separation or directional separation. And basically, it's saying that if 2 nodes are d-separated given a third node, then they are A and B are conditionally independent of C. And this particular property allows us to check whether the dependency among the variables in my BN makes sense, and to also validate the structure. Now, the 2 properties that I mentioned, which is really important, basically helps us to make propagating probabilities through Bayesian networks a lot more tractable. So the classical way of computing a joint probability is given by that first equation there. Then we can, using d-separation and the Markov property, we can simplify it into the equation you see below. So, and that is commonly known as the BN rule. So basically, the joint probability then is expressed as simply the product of the probabilities of the nodes given their parents. Then object-oriented Bayesian networks, which is what we'll use. I won't go into that too much, but it really gives you a way to reduce some clutter in your, if you've got a biggish Bayesian network, it just basically sort of reduces clutter. So you've got private nodes that are just visible to your little model. You've got input nodes that are like placeholders for other nodes to link to. And you've got output nodes, we just make them visible to other models to use. So any questions? I think I saw, did I see something in the chat? Peter?
No, that was Sly talking about from before the Bayesian introduction about talking about how long it would take to go around a network trying to find the validator if there are 716,000 of them.
Okay, yeah, hopefully that's been answered. Okay, so let's dive into the object-oriented Bayesian network that we created. So the one on the left is the object-oriented Bayesian network. You can see it's quite a nice, simple little one. And that box in the middle is expanded to the right. And that really just is a way to calculate the probabilities. So this table performs calculations for the various validator types to become the next proposer. So I won't spend too much time on that. So now that we've got our model, we were able to sort of basically run some scenarios through it. So if initially we just don't do anything, we just run the model, we see, as we saw in that earlier sort of diagram that I showed, that the validator set will reduce to 329,810 from 716,800. And the proportion of validators that will pass the proposer test is 20.8%. And the marginal probability across the various validator types in the validator set of being selected as the first candidate is 26.4%. Being the proposer of the next block is only 0.69%. And if you cast your mind back to that conditional probability I showed you, you can see kind of a reason why, because the only time that you actually get through is if you are chosen and you pass the test. Yeah. Then we ran another scenario. So let's assume that we disregard the staker's sort of strategies. We enter evidence. And so the way you enter evidence, there's several ways, but the one where you just say 100% I've observed this, what are the consequences, and it propagates the probabilities through the BN, is say say all of the validators in the validator set are 64 ETH, so they've just doubled up on each validator there. And you can see the validator set obviously has been reduced to pretty much half of what it was. And then clearly the probability that a 64 ETH validator is chosen will be 100% because that's what you're doing. And the probability for a 64 ETH validator passing the check is 3.12%, and being the proposer for the next block is 3.12%. Then I ran another scenario and I thought, well, right, let's look at the maximum contraction you could have on a validator set. And then, so every validator we have is a 64 ETH validator, and that reduces the validator set right down to only 11,200. And then you can see from the bottom there that the probability of passing the check of being the proposer for the next block is 100%, as we expected, because the equivalent scenario would have been a 32 ETH validator. Currently, the maximum effective balance is 32 ETH. So if you select it, you'll definitely be the next proposer. So, and then I thought, well, let's look at, your validator set consists only of small scale validators. And in that example, basically they mainly consolidated into a twofold validator, so 64 ETH, or they left them as single validators, but a small number compounded to 160 ETH, so five times the 32 ETH. And here the validator set had a pretty good reduction too, to 458,000. And the proportion expected to pass the proposer test is 3.44, and the marginal probability across the three validator types in the validator set of being selected as the first candidate is 38.75, and the probability of being the proposer of the next block is 0.88. We used BN modeling software from Hugen Expert to build the model, and we chose them specifically because they've got good object-oriented capability. And they very kindly offered to host the model for us online. So there's a link there as well, and if you want, I can click on it. And you're free to play around with it, and you can run through the scenarios I've just run through. And then to the right is the blog post that I wrote, basically on pretty much on the information that I've presented today. So we can try and, yep. So this is the online model. If you click on that, it's basically hosted on their demo site, and one of the examples in their demo. So this is live, and you can sort of play around with it. Oopsie, that looked a bit funny there. So probably forgot your person doing it is in Denmark. Yeah, it's gone better up. What do they say? The curse of presenting live. Yeah, so if we say the one we just did, small scale validator, as you can see, it then changes it to red, and you can look there at what that is. You can reset it. You can see here that is the number we started with, and that is the adjusted total. So they hard-coded in for this model. But yeah, it just gives you, if you do want to play around with it, and a link to the post as well. And then basically some of the references here. So there's also a link to the GitHub. So we've got a public GitHub repo with just some of the stuff in there. I plan to add a bit more to it, but you're welcome to play around with it, add it, do it. Or whatever.
Sandra, we're only seeing the model proposer selection webpage. Yep.
Okay. Right. So basically there's a GitHub link, and so there are a few modules there, like the negative binomial and proposer selection. I think I still need to add a few more to it. Because the sort of the generation of the random bytes from the spec, Roberto is now on the call, help me with, and I still need to add that up. That was done in Python. Yep, and then just acknowledgements. That, as I said previously, it was joint work with Kerry, Anders, and Patrick. And it was also partly funded by the Ethereum Foundation academic grant. And just want to acknowledge that the Basia network model we developed is being hosted by Hugen Expert. And we had a review and feedback from many of our colleagues at Consensus and collaborators, including Ben Edgington at the time from Consensus. He's now with Optimism, I think. And Barnaby Mono, Mike Noida, Michael Kalinin, and Roberto. And then I think we're going to be handing over to Peter with his very creative merch store.
Yeah, which is back
New
online.
designs.
The linkage between YouTube and Fourth Wall has finally been resorted out. So it's now easy again to click and buy stuff if you do so wish. Next slide, yes. And so we've got Alex Pruden coming along to talk about his thoughts on the economics of zero knowledge on Ethereum. So talking about, I think, zero knowledge rollups and other zero knowledge systems, and just how does it work? How should you think about it? So I think that will actually be a super interesting talk. The Austin is coming along a little bit after that to talk about EIP-7251. And it's funny, when this talk was first proposed, I was, yeah, it sounds interesting and novel, but I'm not too sure. But, you know, all right, let's run with it. And then since then, some cross-chain experts and myself at Immutable have talked about, oh, yeah, we really should have a look at EIP-7251. And I said, wow, have we got a talk coming up for you? Okay, layer 0 V2. I've got to re-engage with the speaker for that, because the person who was going to deliver the talk no longer works for layer 0. They've moved on, happy circumstances and everything. But I think we're going to have the CTO give that talk. And then in June, I'm going to give a talk about random number generation on EVM-based blockchains and rollups, and the complexities of it and joys of trying to actually do it, so that, you know, if you had $1 million at stake, how would you really do this? And so I think it's really interesting, and particularly, so given I'm coming from Immutable, where we're developing a games platform, and, you know, people want to be able to, say, issue a random NFT and be able to show that it was really not biased by the game or someone else. There's no one attacking you, trying to diddle you. So I think it should be interesting. Yeah, let's look at the next one. Yeah. So if you're here today, there is a YouTube channel. And if you're on YouTube and you think, someone should have asked Sandra this really tricky question, then, you know, come to future talks by coming to the meetup, and you can find out it and go to the meetup link. There is a Slack workspace, and for some talks, there's example code as well. And I think that's about it. So Sandra, thank you very much for a great talk. Yeah, so do you think that EIP or ERC, no, it's an EIP, isn't it? Because because it's core protocol. Is that, and do you think it's going to get up? And, you know, when do you, which fork was it going to land in, do you think?
It seems to be slated for the Electra hard fork, and I think there's a lot of commitment there to make it happen. There are still some minor, I think they're fairly minor issues to sort out, but there are still a few concerns and edge cases that need to be looked at. I know that I intend doing a bit more research into that. But yeah, it does look promising, but it does what appeared to be a very simple change. While it's simple to communicate, but it touches so much of the code base, and I think that's been the concern, and that's why a lot of testing needs to happen, and a lot of eyes on the changes.
Sure. Does anyone have some more questions for Sandra?
Yeah, I had a question. So what future directions do you see stemming from the work that you've done so far?
I don't know if it's self-contained within I mean, the only future direction is sort of writing up what we've done, but I'm trying to think as far as the modeling goes. It's sort of specific to propose a selection. So it would really be, I suppose, doing similar modeling on other issues that are around, or looking at different angles. But
yeah, if I may butt in on that point.
Sure. So
Sandra, because it's very recent work, Sandra hasn't mentioned it quite rightly because it's really my work. I'm a mathematical economist. I'm sure nobody knows me here. So I'm very much about my approach is theorem or lemma proof, make predictions that are theoretical. Very different to what we've seen today, obviously, right? So I do have preliminary results, which would give us predictions on what will happen under EIP-7251. And it's available. I mean, I think it's in the private repo instead of on the public one, I guess. But basically, you'll get full consolidation, and it's an optimal strategy to spread as a staker, to spread your wealth or your stake across all validators to maximize your probability. Because what Sandra spoke of today is the probability of a validator being selected, but we haven't spoke about what's the probability, because what is the staker we ultimately care about as economists, right? So if you put your economics hat on, what you're going to care about is what do stakers do. Stakers can choose how many validators they're going to participate in. Stakers can choose how much how much to stake, obviously. But if they can maximize their probability of being selected or being being a proposer, right? Just specific to the proposer. If you ignore all the other stuff like the slashing and all this other stuff that's going on, which was not discussed today, but Sandra's working on that, I believe. If you just focus on proposer selection, it's fairly easy to see that I can increase my probability as a staker by diversifying across multiple validators. And that works because of the linearity that Sandra highlighted today. So you get this linearity in the probability of being selected. So then you can use that to show, this is the result that I've got, that you're better off spreading yourself thin. So my predictions are that if you're it will not be good for solo validators, right? Because I'd be better off spreading myself off across many validators if I'm a solo staker. So there won't be many solo stakers because I can spread myself across many validators and increase my probability of being selected as a winning validator, and it won't affect my return. Yeah. And this is specific to the current EIP. And moreover, validators. Then you might want to. Which validators do I want to participate in? Yeah, that's the other. So stakers can not only choose how many, it's which validators do I want to join? We're talking about coalitional game theory here, right? So I'm going to join the validator. I'd be better off joining the validators that guarantee me the highest probability of being selected to be a proposer. That's fairly easy to see as well, because I want to, if I want to make sure that if I'm at the front of the queue, I'm going to win. That shuffling process that Sandra so clearly described earlier. If I want to make sure that if I'm at the front of the queue, I want to be as large as possible. I want to join the validator that's as large as possible to ensure that we don't go further down that complex chain of probability events. The biggest one wins. But you don't want to be at the maximum. Why? I'll put the question to you. I mean, you can sort of see that because of the compounding, right? The compounding means that you want a little bit of headroom. And then you can use that, you keep on clearing a little bit of, leaving a bit of headroom to allow for compounding of your stake. That's at the validator level. So once you allow for fractional, because there wasn't much discussion today about fractional ownership of validators, I think once you allow for fractional ownership, my predictions are that you'll get an awful lot of spreading across validators by stakers, and you'll get very large validators, so near the maximum. So it's sort of like a purely on the basis of proposer selection economics, not talking about punishments or slashings or any other factors. If you just focus, ceteris paribus assumptions, for anyone who knows about economics, you assume everything else remains equal. You focus on just this one area, this proposer selection economics. Yeah. So, I mean, Sandra is clearly a fantastic statistician, and I've learned so much from her. I'm the economist in the house. I had to put my 2 cents in. So, yeah. Okay, I'm done. I'll step off the soapbox now and hand it back.
When do you think that this thing you are working on will be publicly available?
We're aiming for a deadline of the thing that I'm talking about. Yes.
Yeah.
Okay, so there's a 16th of April deadline, I believe, right, Sandra, for a conference.
That's right.
Yeah.
Roberto's got 2 papers that he's submitting to the same conference. So
there we go. So we'll try and make that deadline and get all the proofs ready by then.
Okay.
Okay, thanks.
That was actually really interesting, Patrick, because I naturally assumed that we'd all suddenly have 2048 ETH validators everywhere. But you've said essentially we're going to end up with, I don't know, 2020 ETH validators, or something like that.
Yes, yes.
Yeah.
But yes, so very few solo stakers. It's obviously going to be, I think that's the other sort of, you want to spread yourself across as many as possible. So basically you've got a probability of 1 of being in the next validator proposer. You know what I mean?
It's super interesting, like, because it's one thing to think about, but then, how do you actually do the application? If you're actually going to run a validator, not that I've got 2048 ETH to put into a validator.
Yeah, it becomes a matching problem for them, right? They want to try and match so that they can maximize the size, or almost maximize, near maximize the size of the validator. I think that'll be the game.
Yeah. Wow. So there you go, Sandra. So anyway, it sounds interesting. I know I've learned a ton in this talk, Sandra, and thank you for your additional thoughts there, Patrick, because that's also just helped to crystallize some things. All right.
Thanks to Sandra. She's been a wonderful organizer, wonderful to work with. I recommend it to everybody. Just a super manager of the whole thing, and got everything done. Thanks a lot, and to everyone else.
It's been a pleasure working with you. Look forward to the results of your program. Yeah, exciting.
Mm-hmm.
All right. With that, thank you, everyone. Thank you again, Sandra, and see you all again in 2 weeks' time.
Awesome. Bye, everyone.
Bye.
Bye.